All right, start out with any questions? Silence this before it goes off. 2 minutes.
What's all gonna be on the test?
Everything.
Everything.
Magnetism onwards, so chapter 31? 30? Whatever the chapter labeled magnetism is.
Yeah, 30.
Or- So 30, 33, 34 we touched on a little bit. The derivation of the speed of light, that's technically chapter 34, so that part of it matters. And then we jumped to 39, I think it was, the relativity. Would you like me to confirm those numbers?
No, you're good, I'll look it up, make sure.
We had a master set, I believe, for each of them except for the relativity. Any other questions? All right. I want to hit a couple of miscellaneous relativity topics first, and then we'll do a little quantum, some quantum physics, teach you to question all reality. All right. I made the statement at some point, I asked the question of, is there anything that's the same for everybody? That regardless of the reference frame, and I said there were two things. One was the speed of light, and the other one is a relationship, which I did a quick and dirty derivation of, that c times the change in time minus the change in position is a constant. And so I want to actually just show that this does hold true. So it's a constant, so I'm just basically going to start out with a prime there. For no particular reason other than just my preference for the way I want to do it. Because it doesn't matter which reference frame it is, it's either they're primed or not primed or double primed or whatever reference frame you want to use. And then the Lorentz transformation tells me that x prime is equal to, I can learn to make it gamma, gamma x minus ut, t prime is equal to gamma t minus ux over c squared. Where u is just how fast the primed frame is going relative to the unprimed frame. And typically, the way I would draw that is I have some frame s, and then some frame s prime, which is moving at a relative speed of u. So if this is a true statement, I should be able to plug these in for my prime values right there and get the same answer. I do want to amend this, or extend it. This is for a particular event happening at some location and time, and this deals with change in time and change in position. But recognize if I'm dealing with a change in x here, or a change in x prime, that would just be gamma times the change in x minus u times the change in time. So we can easily just use that equation and just look at two different instances, final minus initial, and you get to this. Likewise, delta t prime is just gamma delta t minus u delta x over c squared. All right, so let's do a little bit of alphabet soup here. We'll just throw that stuff into that and see what comes out of it. Hopefully it'll come out as c delta t minus delta x. So we have c times delta t. Oh, oops. Starting out with the mistakes already. They've been really nice if someone said, hey, wait a second, there's a problem with your equation right there. Square. At least it's not requiring a wholesale change. All right, so we have c squared times delta t squared, so that's gamma times t minus ux over c squared minus x delta x prime squared. Oh, I'm just getting sloppy all over the place again here. Delta x. Minus gamma delta x minus u delta t and all that squared. And now we just sort of extend it. C squared delta squared times delta t minus u delta x over c squared minus gamma squared delta x minus u delta t squared. Now I am going to use a notation here because I'm going to be squaring delta x. If I write delta x squared, I'm just going to use that as shorthand notation for delta x squared. I'm not looking at the change in x squared, I'm just squaring the change in x. So I end up with, well, gamma squared. At this point, you should be familiar enough with it. What is gamma?
1 over the square root of 1 minus beta squared, or b squared over c squared.
I'll stick with beta squared for right now. So therefore, gamma squared is just 1 over 1 minus beta squared. And so I get c squared times this squared, and the whole thing's going to be 1 over beta squared. Matter of fact, they're both over it, so I'm just going to extend my fraction bar. And so that squared, come on. What is this squared? This binomial?
Delta t squared minus
U squared x delta squared over c to the 4.
I'm going to put that over here. It would be plus because the negative squared. There's another term in there.
and then delta t
Oh, yeah.
times u delta x c squared squared, the whole thing.
Times 2.
Times 2.
Oh, 2.
It's the outer and inner of the foil
Yeah.
that just add together. I'm going to write that a little bit more neatly. Because rumor has it that I was taught how to write neatly at some point in my life. Minus 2 u delta x delta t over c squared. So it's 2 times the product of that, plus u squared delta x squared over c squared, minus, oops, c to the 4th. Devon had that right. And the Lorentz factor squared is already reflected right there, and we're left with delta x squared minus 2 delta x u delta t plus u squared delta t squared. Let's go ahead and distribute the c squared and the negative sign, so we just get a giant stuff on the top here. So I get c squared delta t squared minus 2u delta x delta t, because the c squareds cancel out, plus u squared over c squared delta x squared minus delta x squared plus 2 delta x u delta t minus u squared delta t squared. Nope, guess I don't need the parentheses there. All over 1 minus beta squared. Can we get rid of anything?
The 2u
Mm-hmm.
delta x delta t.
Yep. Which is fortunate. And so now what I'm gonna do is I'm gonna get I got a delta t there, I got a delta t here, or squared, and then I got some delta x squared. So I'm gonna get the delta t squared terms together and the delta x squared terms together. Because ultimately, I'm gonna have the delta t by itself, the delta t term, and I'll have the delta x term. So I have c squared delta t squared minus u squared delta t squared plus, then I've got this u squared over c squared delta x squared minus delta x squared, all over 1 minus beta squared. And now I'm just gonna factor the two different parts. I'm gonna factor this and I'm gonna factor that. Ultimately, I'm gonna factor out c delta t squared and I'm gonna factor out delta x squared. So in the first one, when I factor c squared delta t squared out, I'm left with 1 minus u squared over c squared. Plus, and then I factor out, actually I'm gonna factor out a negative delta x squared. And I'm left with 1 minus u squared over c squared. And u squared over c squared is beta. It's how fast the primed reference frame is moving relative to how fast S is going. And so this and this cancel out with that, and I'm left with, as advertised, c squared delta x squared minus delta x squared. So c squared delta t squared minus delta x squared is basically equal to the same thing with primes. So for those skeptics out there who didn't believe when I said it the first time, it's just the beautiful nature of relativity is that the fact that there are some things that it is predictable, somewhat. All right, any questions? How far over does it go? Is my left hand still in frame?
Yep. Right there.
Stop right there.
Not there? All right. We're gonna employ that t prime is equal to gamma t minus u x over c squared. Now remember, u is how fast the prime frame is traveling relative to your reference. So in the classic problems that I do, u would be, for example, the speed of the rocket relative to the Earth, if we consider us the S frame. What does dt prime equal? So 1?
Just gamma.
Okay. No, not gamma. Are you working it through your head first before?
Because I know you gotta deal with that T that's in there.
Yep, I got an X in here too.
The X shouldn't matter. Well, no. Yeah.
I don't know if it would help to look at a sort of macroscopic version of it. We can do it the long way, there's no problem with that. I can use product rule, I'm multiplying gamma times this other stuff. So let's go through it that way. So this is the derivative of gamma t minus u x over c squared, which would be d gamma times t minus u x over c squared, plus gamma times the derivative of this, which would just be dt minus d of u x over c squared. All right, so let's take it bit by bit. Gamma, constant or variable?
Constant.
Yeah, it's constant because S prime is traveling at a constant velocity relative to S. If the prime frame were not traveling at a constant velocity relative to here, then it gets a little bit funky trying to deal with it. But then we're branching into, either we have to look at very specific moments in time, or we have to bring in general relativity, which I don't wanna do. So, d gamma here is 0 because gamma is a constant, so that whole first term drops out, so I am left with gamma. And then over here, dt minus u is how fast the prime frame is traveling, it's constant, c squared, it better be constant, otherwise all of this that we've been doing the past couple times is bunk. So we'll just u over c squared times dx. If I factor out dt, we end up with dt prime is equal to dt times gamma 1 minus u over c squared dx dt. So dx dt would just be how fast, would be the speed of an object in the x direction. We'll stick with the typical brainwashing, in the x direction of some object from the Earth's point, or from S point of view, or the Earth's point of view. There are classic problems. Dx dt is just how fast that object is moving relative to us. All right. When we dealt with the relationship between velocities, when we did when we when we found the relative velocity in a prime frame versus the original frame, we dealt with objects that were moving, or at least the example I did, I dealt with an object that was moving in the parallel or anti-parallel to S prime's movement. Now I want to deal with what happens if I have my S frame and my S prime frame traveling to the right, but I have an object that's moving in two different directions here. Let's see if we can get the stunning visual effects. Ooh, there it is. Establish I and J. So, when I have an object that is moving, again, it's not accelerating, it's just moving at some constant velocity, and we'll call this Vx and Vy. So, the velocity of this object, let's call it P, or particle, is Vx I hat plus Vy j hat. And none of it's primed here, so this is in the frame of reference of S, Earth, if you like, or whoever the observer is that this. I'm sitting here on Earth and I'm watching this object move. Now, in the S prime frame, we have a mechanism for dealing with what Vx prime would look like. But in the Vy frame, it's a little bit different. Vy is just, in the prime frame, would just be the change in the y value in the prime frame over the time. But the length contraction, the dealing with differences in length, happens in the direction of movement. So y prime and y are the same thing. Any change perpendicular to the movement of S prime frame is the same to both. So that would just be dy. However, dt prime is not the same as dt. We just went through that. So this is equal to dt times 1 minus u over c squared dx dt, which is just dy dt over 1 minus u over c squared. And dx dt, well, that's just how fast it's going in the x direction, so vx.
What happened to the gamma term?
Oh, thank you very much. Stick it there. Yep, thank you. And dy dt is just how fast it's going in the y direction in the S frame. So this is just Vy over gamma, 1 minus u Vx over c squared. And all of that is dy prime over dt prime, which is just Vy prime. So this is how you would deal with it if we have an object that's traveling up that not parallel or anti-parallel to S prime, how you would actually deal with the other components. And this is going to be incredibly handy for what we're doing next. So questions up to here. Sure didn't skip anything. We're going to come back to this, so I need to write this down. Keep that. And then we have Vy prime is equal to Vy over gamma 1 minus u Vx over c squared. Now, the last time, when I was trying to go through and derive that m is equal to gamma times m sub naught, I feel like my justification for doing that was off, so I just want to go through a simple example here, bring back some really fond memories of 251. And show that there has to be something else different. Again, I'm going to hand wave through one of the conclusions. But so let's just start out with a simple example of I have a 3 kilogram mass traveling to the right at 48 meters per second. It's going to collide into a 5 kilogram mass, and we'll have a perfectly inelastic collision.